Hey friends, welcome back to another exciting episode of Going Nuclear. I'm here with a really special guest. His name is Dr. Markus Piro. He is the Department Chair of Energy and Nuclear Engineering Department, also the Canada Research Chair for Nuclear Fuels and Materials. Welcome.
Yeah, thank you very much for having me.
Well, during my university experience here, I actually was a student of professors in his nuclear fuel cycles course, which was a phenomenal course. So in this conversation, we're going to be chatting all about education frontiers of nuclear, research, and maybe even go deep dive into the fuels, right? Fuels element of what the future of the nuclear industry looks like. So, sir, tell me a bit about this new nuclear renaissance that you're seeing. What's it look like for nuclear education?
Yeah, so for nuclear education, we're starting to shift in a little bit of a different space than we did in the past, and a lot of that's reflected to the very rapid change of events in the Canadian nuclear industry and also abroad. So here in Canada, historically, we've had a number of CANDU nuclear generating stations producing electricity here in Ontario. We have about 60% electricity produced from nuclear power, which is a lot. And the industry utilities have made some commitments to further expand that. There's some recent announcements of the Bruce Power company to add another 4,800 megawatts to the Bruce site. OPG's made a commitment to Darlington B for 4 BWRX 300 units. And outside the province, there's been in Saskatchewan some BWRX 300 units. Looks like they're going to go there. In New Brunswick, looks like a molten salt reactor and a sodium-cooled fast reactor there. And that's just in Canada. So that's a lot already in Canada, let alone what's going on in the rest of the world. So considering here at Ontariotech, we have the only nuclear engineering program at the undergraduate level across Canada, which is pretty exciting. And we have a very robust program that's supported the nuclear industry for a number of years. And, naturally, that was very CANDU centric, right? And with this evolving nuclear landscape, what that means is that we also have to start thinking about how to, look at our undergraduate program and also our graduate programs to best support the industry's needs. And so, some challenges with that. One of which is that, a few years ago when I came here at the university, I remember talking to OPG and they had, I forget what it was, something like 120 different vendors that came to them with, SMR designs. 120, right? You can't, have a program that supports 120 different reactor designs. And then OPG down selected to 3 different vendors, General Electric Hitachi, X-Energy, and Terrestrial, and then ultimately picked BWRX 300 from GEH. So now we're starting to get a little more focus on how that, a little more concrete in terms of how the landscape has evolved. Not fully settled, but getting a lot more clarity there. And at the university side, we're starting to adapt that. So for example, in addition to all the CANDU and the hardcore nuclear course that we have in our program, this year, very excited, we're going to be delivering a BWR special topics course for the first time by Professor Harville.
That's really exciting. Yeah, definitely like a program that's been traditionally very CANDU centric is now evolving. And what would you say is the demand? What does it look like? Are you seeing this increased demand when vendors and utilities approaching the university and saying, hey, listen, we need students and we need them fast?
Right, yeah. So our overarching mission is to provide the best educational experience to our students and prepare them to support the workforce, right? And now that workforce is changing a bit. What I keep hearing from our industry partners is that, they need more employees. Not just engineers, other disciplines as well, science and, non-science or technical programs, but they need a lot of people. I hear that a lot. That's something that we're hearing across the board. And there's a little bit of a chicken and egg thing going on there, right? Where, in order for us to train more engineers in the program, we also have to have more students at the high school level also applying to the program. So if there's any, folks in the audience that might be, in high school or even earlier, the industry is just growing so rapidly, great paying jobs, very stable industry, and all homegrown here in Canada, producing safe and reliable, affordable electricity. So great opportunities for folks to get into from the high school come to the university.
Yeah, absolutely. Tell me a bit about the research aspect in this department. I know you're the research chair in Canada for nuclear fuels and materials. Tell me about the influx and changes in nuclear research with these new reactor types coming to Canada.
Right. So with these new reactor types comes usually the need for R&D in those types of areas. And with any type of research, typically you need to have funding to support the research, right? And so that kind of falls into painting with a broad brush, government level type of funding, and also kind of industry led kind of funding. And we're seeing a lot of it on both sides, right? So there's a lot of interest to support Canadian nuclear needs in research kind of at a high level. Here in the Department of Energy and Nuclear Engineering, we have faculty members that cover all major areas of nuclear engineering and also sciences. So I'll get into that in a minute. We have folks in thermal hydraulics, reactor physics, waste management, corrosion, decommissioning. I'm a fuel guy. Other people are reactor safety. We also have other folks in the department supporting, the other two programs which we have. We're not just nuclear engineering. We have a health physics and radiation science program, and we have folks involved with that. There's 2 industrial research chairs supporting that area, Professor Waller and Atkinson. We also have some folks on the energy engineering side, so not just nuclear, right? So there's folks involved with a lot of research and more energy systems kind of stuff. But I think your question was like research, like how that's evolving with the landscape. It's a bit of an interesting situation because, like I said a minute ago, there are just so many different SMR vendors, right, of many different technologies. And we have finite funds, we have finite resources to cover. We can't do all of them, right? Like we can't do, like say, CANDU, PWR, BWR, molten salt, fusion, all that stuff. That's impractical to give it a really good, the effort that each one of those needs. And part of the challenge is that some of those technologies are very different TRLs, technology readiness levels. CANDU, LWRs, very high. They've been running for decades. However, some other technologies, like molten salts or fusion, for example, much lower technology readiness levels that require a lot more fundamental research, right? So, the funding pathways can be very different for that, and the research needs can be very different to respond to that.
Absolutely, definitely, and I think with new technologies coming into the horizons, I think one aspect that I would love to explore with you is actually nuclear fuels. Right? It seems pretty straightforward of a topic, but when you look at procurement of fuels, when you look at reprocessing technologies that are out there, when you look at even technologies like Dupic, like directly using spent fuel in CANDU reactors.
I was just saying that because we covered these things in my class.
Yeah. So I got a chance to learn a lot of these things from with Dr. Piro's class. And it was phenomenal, like mind-blowing. Tell me about your thoughts on the fuel cycle and how it's changing here in Canada.
Yeah, it's definitely changing. What might help to give, I guess, a bit of context is like looking at where we're at today and where it seems to be going, right? So in the nuclear fuel cycle, what that basically means is what's going on with the uranium every step of the way, from taking it out of the ground, making it something usable that can be stuck into a reactor to generate heat and taking it out. That's obviously simplifying it. But what's worth noting is that here in Canada, we've historically covered almost all of those stages of the fuel cycle. Here in Canada, homegrown Canadian technology and companies supporting that. So as an example, Cameco is a significant player in the field. They are involved with mining and milling, refining. They have a refinery in Blind River. They have fuel conversion facility in Port Hope, manufacturing, both at the pellet level and fuel bundle level here on the east end. We also have BWXT, who is involved in fuel fabrication, and then of course the utilities that will buy that fuel and then cook it up in their reactors to generate heat. And then on the back end is eventual disposal, which is another topic. So we have a lot of that already right here in Canada. Now that is pretty well supporting the CANDU fuel cycle. Your question was how that's evolving to, these advanced technologies. And one of the big differentiators there is the fact that all these other technologies use enriched fuel. And so what that means is that we would, in order to apply that kind of fuel cycle here in Canada, we would need to have enriched fuel. So some of that is yet to be determined on how that works. We have, and that obviously depends on which reactor technology, right? So for example, the Dupic 300 uses GNF2 fuel, low enriched uranium. That's pretty well established in the United States. So that seems to be somewhat straightforward. However, several of the other reactor vendors use HALEU. So that's basically above 5% U-235, but below 20. And as probably a lot of your listeners know, there's a bit of an issue right now with supply chain for HALEU due to the war in Ukraine, whereby Russia was previously the major supplier of HALEU. And so that's obviously changing the supply chain dynamics. And that's a major consideration to think about here in Canada. Like I was saying, some of these fuel technologies are, have different levels of technology readiness levels. So for example, CANDU and BWR is pretty well established, right? And, they're ready to go. So the GNF2 fuel that goes in the BWX 300, that's pretty well at hand. But what's worth noting is that there's, the number of other type of technologies where we don't have any commercially operating plants based on those technologies. It also allows some room for some other things to be considered. And, one thing I've seen a few more at the nation state level, not so much specific vendors, but, some other things that can be considered is, ultimate uranium resources. So, there's a tendency to kind of think in the short term or business case for a specific type of reactor being deployed. But, uranium on Earth is a finite resource, right? And, this introduces some, alternate thoughts. If you're thinking strategically for, let's say at a nation state level for many decades to come or even centuries, it opens up other possibilities of alternate fuel cycles like involving thorium, for example. Not so applicable for commercially operating types of fuel cycles, but if we're looking at some that are still being deployed, it allows for, let's say, a combined thorium fuel cycle to be considered. The main driving force there is that thorium resources are 3 to 4 times that of uranium and could potentially be used. But anyways, so just my own 2 cents.
Yeah, for sure. And I would love to dive into that topic a bit. Uranium, we're told that it's a finite resource and there's only so much of it to go around. And with the world's energy crisis and electricity needs increasing across the world, how far can we stretch that out? And also, are there other reserves of uranium in the world that we potentially are out there and we just haven't discovered?
I mean, that is definitely a possibility. A little history lesson on that was in the 60s and 70s. There's a large scare. Not only do I mean with oil resources affecting gas for cars, but also significant concern for uranium resources, where at the time the U.S. government, for example, was very seriously looking at fast spectrum reactors to get higher uranium utilization. And what effectively, or at least one reason of others why a lot of that was discontinued, was that larger amounts of uranium resources were discovered. So yes, it is possible that more uranium resources may be discovered. All I'm saying is that, with some of these low TRL type of technologies where you don't have a qualified fuel design like you do, for example, for high TRL designs, it opens up the possibility to look at alternate fuel cycles that may be in a nation state's best interest to look at longer term. Yeah,
absolutely. I don't want to lose sight on one other topic. One other topic that I wanted to explore with you was radiomedical isotopes. Right?
For sure.
And we're seeing our CANDU reactors are some of the best power reactors that can also produce medical isotopes. Tell me about any research that's ongoing there. What are your thoughts on?
Yeah, so for there, what I'm going to do is, I hope you don't mind me putting a plug to my previous employer, Canadian Nuclear Laboratories, up in the Chalk River area, where I worked for several years before coming to Ontariotech, and they had a very significant program in producing Moly-99 for medical diagnosis and treatment, among a few other isotopes, and they were a huge world leader in that area. Now the situation's changed a bit. We have medical isotopes being produced at the nuclear generating stations, like cobalt-60, for example. Now we have lutetium isotopes being produced, and this is an important topic, and I think is worth pointing out to also the general public how important these things are. Where these nuclear generating stations are quite literally producing materials that save people's lives, right? So there's depending on which particular isotope that's being made, there's a good chance it could be made here in Ontario. And that's pretty amazing how you have something that is so impactful to a person's life. So that's pretty cool. Now the way that these things are made can vary quite a bit depending on the isotope and the machine generating them. But it is pretty important. We do have some courses here as well on medical isotopes and that touch on those topics.
Definitely a really underplayed topic, I feel, in the general public's eye, right? Nuclear radiomedical isotopes, helping with cancer therapy, with the sterilization of medical equipment, right? So it's pretty phenomenal, like the different uses of these isotopes. One topic that I really enjoyed during your course was actually Dupic, so direct use of spent fuel, pressurized reactor spent fuel in CANDU. It just really blew my mind that spent fuel from one reactor type, low enriched uranium, can go right into a CANDU reactor and operate like fresh fuel. So tell us a little bit about Dupic, and maybe is there potential for Dupic in the future?
Yeah, so this was one topic of one lecture that was covered in that class, and I threw it out there as well because I thought it was a great example of great engineering and creativity from. This was originally from the Atomic Energy of Canada Limited in joint partnership. From what I remember, that was Kerry from South Korea, but might be fuzzy on that detail. Anyway, great engineering there. So for your listeners, the basic idea with Dupic, which is I think pretty interesting, is that the spent fuel that comes out of a PWR, pressurized water reactor, it's got a lot of fissionable poisons in it. You can't, while you're burning up the fuel, you deplete the usable fissionable components within it, U-235, and then you also generate these fission products that basically make it harder to keep burning it, right? So there comes a point in a PWR where it's not useful to keep it in there, right? You can take it out and put in some fresh fuel. But what's worth noting is that in a CANDU, it's a very different scene where the reactivity of that fuel coming out of a PWR is actually could be a bit higher in some cases than fresh CANDU fuel. And the basic idea there to keep in mind is that in the CANDU we use naturally enriched uranium, so 0.71% U-235, and the burned up PWR, depending on the conditions. I think Dupic, when it was originally developed, like in the 90s or so, it's like 0.9 or so. So your fissionable content is higher than fresh CANDU fuel. And then, you mechanically process it, technically not reprocessing, but, and then package it up and put in a CANDU. South Korea and I think China as well, but I don't think it's being pursued anymore. But, I put that in the class because, this is great engineering, right? And great, creativity on how to solve problems. My sense is that it's no longer being used commercially, probably because it doesn't make financial sense, but great case study for students like yourself when you took the class to think about, different ways to solve these problems.
I know there's definitely the economics behind this. It's not a straightforward process. You need modifications on the CANDU side. And also fuel handling is not cheap, right? So what about in the future when Korea and China, they're going heavy on nuclear, right? What do you think that there is potential for them to utilize this technology and for them to have a business case around it?
Yeah, so from a technical side, it works. That's been proven. I think it ultimately comes down to economics. So, that's up to them. Who knows? Maybe we have a few BWRs here in Canada sitting right next to some CANDUs. Who knows? Maybe OPG decides to do that as well. But again, business sense.
For sure. Also, another aspect is there's the business and economics, but then there's ESG, right? Environment sustainability perspective, right? A lot of companies are looking at ESG and they're looking at how can we reduce our environmental footprint. So do you think that Dupic could come out as a solution to reduce the footprint of already small footprint that nuclear has?
I don't know. That's a hard question to ask. I mean, the same could be said about reprocessing recycling, which is not currently done, in a civilian sense in North America, more so in Europe and parts of Asia. With Dupic, I don't know about that. I mean, if you're looking at doing things like reducing the footprint, probably get a little more traction on the reprocessing recycling side, which is obviously very complicated and multifaceted, right? Safeguards and that kind of stuff are major topics there.
So tell us about that. Like a lot of folks in the environmental space, the energy space, clean energy space, they don't realize that spent nuclear fuel can be reprocessed, right? There's recycling benefits, which a lot of areas in Europe, in France specifically, has a lot of capacity around that. Do you think there's movement in that area, especially in the United States or other countries? Are they taking another look at reprocessing and saying that, hey, listen, there's potential there?
As far as reprocessing goes, I mean, I'm not really part of those conversations. My sense is that it's probably more of a political decision than it is like a business decision. Obviously, depending on which nation you're dealing with. It also depends on like what technologies are around where it makes sense. Like as an example, if you're thinking about being purely technical, not political or those other facets. From a technical perspective, if you're looking at LWRs, reprocessing makes more sense. CANDU? No. And that's just because you're dealing with a totally different situation. In CANDUs, like you burn up all of the usable uranium-235 pretty early, and then you're coasting off plutonium for a while. And that's a bit of a different story than it would be for LWRs. Or if you're looking at a reactor like a triso fueled reactor, it's going to be a lot harder to get access to your fuel kernels than it would be like a uranium dioxide fueled reactor like an LWR or CANDU. Molten salt reactor, on the other hand, also a different story, right? Where it may be possible to to access fissionable content in a very different way than you do in other reactors, and that starts touching on things like non-proliferation and safeguards, right? So for example, there are some conceptual designs with molten salt reactors that have online chemical processing units, right? So in some of those cases, it may be designed to scrub fission products from your salt, which means that you're basically removing stuff that is reducing you're affecting negatively your reactivity, while potentially adding more fissionable content.
It's a really interesting perspective on reprocessing and the future of that across the world. How it's not only a technical solution, but also there's political underlying political hurdles there.
Right, and that's part of like a national strategy, right? Like, so for example, in France, they have a national strategy in the way that they look at nuclear, and right now they got, pretty sure they're all still operating, but may have changed 58 pressurized water reactors, and they're more or less the same kind of technology. Of course, they're like children, right? Yeah, they'll have their own specialties. But they also have a national strategy that involves reprocessing recycling, whereby the recycled fuel goes back into fresh fuel into another PWR fuel cycle. But I think the whole idea of like a national strategy is something to worth reflecting on here in Canada as well, right? Where historically we had a very robust supply chain across all nuclear, and I don't just mean like components and stuff like that. I mean supply chain involving supply of talent, right? Like students, like the students that come out of our nuclear engineering and health physics and radiation science programs, where we have suppliers, manufacturers, construction vendors. We have consulting companies like Kinetrix, for example, or Stern Labs. We have the National Lab, CNL, the regulator, CNSC. And all of these other things, but they're all like very CANDU centric, right? And I think one of the challenges that we've faced in the last few years with all these SMRs and microreactors coming about is, they're based on technologies that we do not have experience with here in Canada. So what that means is that we kind of, speaking as, from a Team Canada perspective, we have to be able to, rise up to that, right? So what does that mean? The regulator needs to have folks that are competent in not just CANDU, but now BWRs, molten salts, and gas-cooled reactors, sodium-cooled fast reactors. The utilities, they need to have fine expertise to fill in those gaps. The national lab, they need to have research and development in those different technologies, and that's I think harder than people think, right? So because Canada, we have limited resources, about roughly 10% of the population GDP of the United States, right? So we can't throw money at all of the technologies like the US can, right? And how do we balance things, right? If the Generation 4 International Forum, GIF, has 6 Generation 4 reactor technologies identified, we can't throw money at all of them, with equal investment. And, if there was a period where we put in, Team Canada put in a lot of money into supercritical water reactors. That was the technology that was selected. But now we're also at a point where the nuclear landscape is very different than it was 10, 20 years ago. There are no vendors in Canada based on supercritical water reactor technology. So that means that we gotta shift gears, right? So seems like a little bit of reflection is needed, I think, and how do we approach that with evolving technologies? Not just in response to the last several years, but how do we think about that moving forward, right? Like if we're actually serious, for example, in fusion, right? How do we balance much lower technology readiness levels versus high TRL technologies? Definitely,
those are definitely all things that are really important to consider. One thing that always comes to mind is, for example, BWRs, boiling water reactors. We don't have expertise in that, right? So
we're growing it.
Is there potential for, collaboration with countries like States, but also, countries like Japan, which are like BWR heavy, right?
Right. So at least I'll speak on the university side. So in my own experience, for example, putting on my researcher hat, we've partnered with external collaborators on those different technologies. And that's, a good way for Team Canada to, leverage those great partnerships in these new technologies and bring that up. So we had one with Nippon Nuclear Fuel Development in Japan, for BWR Fuel Development Company, and also various BWR efforts down the States, including the Sandia National Laboratories. And those worked out really well. Same was true. We did research with a number of other partners down in the States, including Oak Ridge and Idaho National Lab, on various other type of advanced reactors where graduate students and postdocs will be working on those type of R&D efforts. Often they do like an exchange down in the States and then come back up. And the Canadian nuclear industry hired those people to then work in them. So that seems to be, at least through the university lens, one pathway to developing more of those capabilities and advanced technologies here in Canada.
Nice. That's that definitely is important. Looking at things from a graduate level perspective, what is the appetite for students nowadays pursuing graduate level programs, and also for the industry supporting students? Because I know with a lot of industries, utilities, a lot of vendors, they'll actually fund a master's program. Tell me about the whole landscape there.
Yeah. So, for myself, I'm fortunate to get some really great grad students, very skilled, very knowledgeable. You met some of them earlier today. And they have some great projects. A number of them work closely with industry partners. And so there's definitely, a lot of those folks that really love doing research. They come in and they do their projects, which is great. That's also balanced on the other side, where the nuclear industry is just growing so much here in Canada with great jobs that people, the students at the undergrad level, they're just inundated by these great job applications. More reason for our high school friends on the line to apply to Ontariotech and get an education in nuclear engineering. So with all of the industry is doing so well and hiring people, that, there's a bit of a challenge in getting a lot of graduate students, right? And so, at least domestically, the appetite on the international scene is still very high. We have a lot of folks applying internationally that want to come to Canada, which I think is a great country to live in and do their education. So we still get a lot of that. Your second point, I think, was about industry, support of their employees doing studies. What's worth noting here in our department here, we have multiple programs, not like the traditional Masters of Engineering, Masters of Applied Science, and PhD levels, which you kind of get everywhere. We also have what's called a graduate diploma program, and we have industrial training program. So the room that we're in here is actually meant for the industrial training program. So your audience here, they might see all these computer screens behind us. This is actually a simulator of the Darlington Nuclear Generating Station that's used for industrial training. And the graduate diploma program will take, let's say, an engineer that might be a mechanical, but let's say their employer wants to bolt on the nuclear side of things. So they'll come into the graduate diploma program for a year, and then we'll give them all of the hardcore nuclear stuff that they need to be successful in their jobs. At the MEng and MASC levels, and also even PhDs, I have, for me, putting on my researcher hat now, I have a bunch of students that are part-time working in industry while doing their graduate studies with us. So we have folks from OPG, Bruce Power, CNL, and Kinetrix. I think I got them all. They're doing part-time studies, at least in my group, and there are other groups in our department that do that as well. So, they might be working at the plant 9 to 5, and then afterwards they might do part-time studies with us, take some courses, do some research. So pretty exciting.
It's phenomenal. No, it's definitely really cool to know that for especially those listening in, that you can do your 9 to 5 and then afterward pursue a master's, pursue PhD, and kind of continue your studies. So
like what we've done for a number of the courses is we would, not always, but for a lot of them, we would do them in like hybrid mode. So they would be, you'd have an instructor in person in the room doing like a kind of conventional lecture, but your audience probably can't see it, but we have all these high-tech microphones on the ceiling, and also a dozen or half a dozen projectors up on here, so we can have multiple screens going, multiple cameras going, and we have it all recorded to an online system. So they can, folks could watch it live from home or from the workplace, or even watch the recording at night after their shift. So like I've had, one student, he's been up in Bruce, and I don't think he's been here throughout his whole grad studies, and he's doing like trials of fuel modeling with me.
Nice. That's really good to know. It's good to know that the education is available, and in terms of wherever you're located, right? There's no hurdles there. So it's good to know for those listening in. One other topic that I wanted to explore with you, sir, is safeguards. Right, safeguards is a pretty important part of the industry, right? To make sure that materials, especially spent nuclear fuel, is not being diverted for use of nuclear weapons, right? Tell me a bit about these new reactor technologies that are coming out, like molten salt reactors. There's TRISO. There's going to be different safeguard approaches that are going to be taken. Tell me about the challenges and maybe even opportunities that are there.
For sure. First of all, I don't consider myself a safeguards expert. I'm a fuel guy, but obviously there's touches on some of this stuff. I think some of the challenges and opportunities are very vendor specific, but so I'll try to be as generic as possible. And I think there's some challenges and opportunities. So like right now in CANDUs, for example, we'll have individual fuel bundles about 0.5 meter, 18 inches long, 4 inches in diameter. And each bundle has a physical stamp that's stamped in metal so that there's a unique identifier, just like you'd have, a unique identifier in your license plate of your car, right? And that bundle, there's a record that is put to that bundle throughout its whole history, right? When it's manufactured at the plant, let's say at the fuel plant, going into a reactor, its history in reactor and then going out. And, that's pretty well established. And, safeguards, inspections, there's additional measures like video cameras and other type of detection techniques to track where it's going, right? That gets a bit different when we start talking about some of these other reactor designs. BWRs, again, high TRL, pretty well established. So I won't touch on that. Same with PWR, right? But when we start thinking about some of these other reactors designs, like let's say if you have a TRISO fuel design, how do you do that, right? How do you identify each, some vendors will have a pebble, so it's roughly the size of a baseball. Some vendors will use pellets, like as a fully ceramic microencapsulated TRISO pellet. How do you deal with that? I've seen some cases where they'll actually like 3D print a QR code, or this is what's proposed, not commercially operating yet, with a 3D print like a barcode into the pellet. I've seen that before, and I've seen some other pretty, more sophisticated ways to kind of CSI kind of backtrack a pebble, that gets a little complicated. So I give those two examples where, even for those, I don't think it's fully resolved yet, at least not like to the commercial level yet, right? But what that also means, you start getting some interesting, creative engineering designs. Like I mentioned, QR code, that's kind of interesting. See how well that works commercially. Then you also have other designs like molten salts. I'll mention this again, where in the molten salt sense, there are different vendors with different designs. Some vendors will have like a giant core that's just where the salt is both coolant and fuel. That's all liquid. How do you control that? It's very different than having a bundle where everything's physically contained in a bundle where you can track that physical bundle and also have good predictions based on qualified codes of what its contents are. Now, if you have an entire core of a molten salt reactor that operates for several years, you can control that whole core, but then that means you have to control the entire core rather than a small subset. There's other designs that would take like a physical barrier between the fuel and the coolant, where you can control that a little bit better. I kind of go over these things because there's many different challenges on a safeguards perspective, depending on the technology.
Absolutely. No, those are some really cool designs, right? A QR code on each pebble, and so those are some interesting challenges as well. One more thing that I wanted to explore with you, or one additional thing, was going back to fuel cycle. I've seen that Cameco has recently acquired Westinghouse, right? And so
49%.
Sorry?
49%.
49% of Westinghouse, right? So tell me a bit about the fuel supply to Canada, right? Canada is going to be utilizing lightly enriched uranium now. There's going to be more regulation around that CNSC regulation. There's going to be different approaches in terms of handling the fuel, in terms of how the fuel is transported in, how it's stored. Tell me about the complexities and the challenges that Canada is going to face with this new fuel type.
Okay, so I guess it's more specific to GNF2 fuel for the X300?
Yes.
Okay, so I'll try to be careful with this as well to avoid any sensitivities. So in the public space, a lot of details are not publicly available. Where some of these decisions are likely made in I would say like a proprietary framework at the moment, but some possibilities that could be had is where the fuel is, let's say, manufactured in the States as it is now, and then shipped to Canada. Another possibility, who knows, is that if eventually we get to the point where the fuel is manufactured in Canada, which would require new fuel fabrication facilities, whether it's Cameco or whatever else. And it also begs the question, let's say if we do manufacture the fuel in Canada, where we would have to have enriched fuel, right? So where would that be done? Whether in the States or do we look at an enrichment facility in Canada? And again, that comes back to the national strategy thing, where it's not the business decision is one side, but there's also political factors as well to be considered there. So I'd say at this point, kind of remains to be seen. The one thing to note again is that particular design is pretty well established and has a track record.
Interesting. Yes, so sir, definitely some really interesting technologies there with enrichment, and I guess we'll have to see what the future holds. So back to the whole Team Canada approach with the nuclear industry, right? We've seen Canada do it the first time, right? We've developed our own indigenous reactor design. We've exported it to countries across the world, and we've really set a really positive precedent for how a country can develop such an independent supply chain. And now this is kind of flowing into Team Canada 2.0. Tell us about that.
Yeah, so I'm a born and raised flag waving Canadian, and love to see Team Canada 2.0 here in the nuclear world, and where it looks like, at least from my humbling, I guess, perspective, is that things are moving pretty quickly, especially where it's being led, I would say, more in the utility space, right? And in terms of deploying some of these reactors, There's still a lot going on and some uncertainties about how we evolve, but a lot of things I think would be pretty exciting, and I think that part of that excitement will also manifest in some different ways. So, for example, having clean, reliable electricity is one thing. We've seen that. We've seen, the production of medical isotopes for the diagnosis and treatment of cancer. Pretty significant impact there to the world and to the Canadian people. And the last one, what I think is something that we'll see in the coming years is how that affects the quality of life for folks, especially with things like micromodular reactors in remote communities, if they end up getting deployed, where you no longer have, let's say, diesel generators being used in very remote communities where the cost of diesel is enormous when you have to transport it up there. But having a reliable source of electricity where you don't have to worry about it, to some degree, where you can just have it running for a while, but also producing, generating, excess heat that could be used for alternate things like, district heating or for greenhouse facilities, so you can actually produce, vegetation in very remote areas. Some of these things could have pretty significant positive impacts on people's lives. So I think that's pretty exciting. And, tethering that as well with the ongoing responsibility that I think we all have to feel in the nuclear industry, that, the reason why the industry has been so successful is by very concerted due diligence to the quality and integrity that we do as professional engineers to the profession. And, I think that is part of the whole integrity of the Team Canada approach.
Great. I really enjoyed this discussion. We hit so many different points, like, nuclear fuel cycles, the future of Canada's nuclear fuel scene, right? And reprocessing technologies, and to end it off, how Canada's overall national strategy. So really appreciate this discussion.
Yeah. Thanks for having me on the podcast, and also great to have you back at your alumni here in Ontario Tech. Great to see you.
Thank you so much, sir.
Thank you.